The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
I'm Shiraz Tayabji. I'm a senior principal engineer with Applied Research Associates. I've been around concrete pavements for a long time, more than I would like to remember. Anyway, I appreciate the opportunity to talk about my favorite subject over the last few years. It's precast concrete pavement technology. I appreciate the opportunity to make this presentation. Everybody who is driving around in an urban area knows the problem. We've got significant amount of traffic in all urban areas. Our pavements are 40, 50 years old. Ever since the interstate days, many of these pavements have not even gone through a first cycle of rehabilitation. Many of these pavements have been repaired, of course. But this is a serious situation. So most of the highway agencies are facing this situation every day, and the question is, how do we repair or rehabilitate? Okay? We can do short delays. Typically, we want to do much of this work in urban areas during nighttime or very short closures, lane closures. So we have been using rapid setting concrete, but it has not given us consistent performance. Sometimes it's a hit or miss type situation, and we cannot rely on it for our long-term solutions. Anytime we do any of this urban repair or rehabilitation, we are expecting this repair and rehabilitation to last, at least in the repair case, for at least 15 to 20 years. For rehabilitation, we treat it as a new construction. We are expecting a service life of 30 to 40 years. When we are using rapid setting concrete, sometimes we have to go back after 6 months or within few years. And we cannot afford to do this fix to fix all the time. When we want to do it well, we can do it with conventional concrete, but it requires longer lane closures, which we cannot afford to do. What we need is shorter delays and longer service life. And we feel precast concrete pavement can provide that. Okay? And so I'm going to give you a background on precast concrete pavements. How many of you have seen any precast pavement construction? Few of them, so I can at least tell you some long stories. But I'll give you some background on precast concrete pavement technology, the systems that have been developed and the applications using this technology, and then as time permits, we'll talk about some case studies. So just a quick definition. These are systems fabricated and assembled off-site, transported to the project site, installed on a prepared foundation. System components require minimal curing time. So basically, we are placing these panels during the night time. We are opening to traffic in the morning. We may use some patching material. We'll talk about it, dowel slot patching material and so forth, that gains full strength within 2 to 3 hours. So in some cases, we do have to wait for some of this patching and grout materials to attain strength. But we are talking about maybe 2 to 3 hours. And we can also do this insulation during up to inclement weather condition, but if it's light drizzle and so forth, we can still go ahead and place our panels. So the systems are application ready for rapid repair, rehabilitation, reconstruction. We are also using it for asphalt pavements in terms of at intersections and so forth. And typically, as I mentioned before, lane closures at night and open to traffic by 5 to 6. Okay? So it's a recent technology. We have done some work in the US in the 50s and 60s and 70s, a little bit of experimentation here and there, but the technology was never right or ripe to do large-scale implementation. In Russia, they've been using precast concrete pavements since the 1950s. In Siberia, there were thousands of miles of precast concrete pavements. In Japan, they've been using it also since the 1960s for airports, tunnels, and freight yards, and so forth. But in the US, in mid-1995, we said our traffic situations are serious enough that we have to come up with some different strategies for overnight repairs, rehabilitation that would last longer time. So since about 2001, we have started doing what we would call production projects. Many states are now routinely using precast concrete pavements. Many states have done demonstration projects and learning from this technology. So as I mentioned before, all the panels are fabricated off-site, brought to the project site. Only minimal fuel curing is required, nighttime work, short work windows, and typically you are working on a single lane at a time. If you have more lanes, typically for a single lane, we have to have 3 lanes. 1 lane for shipping panels and 1 lane to maintain traffic. We are almost never going to shut down our highways to do any of this repair. So we are always maintaining some traffic. So just quick history. I'm not going to get into too many details, but FHWS started getting interested and started funding projects in the mid-1990s. Highway agencies started looking into it since about 2001. Industry got into the act, and there are lots of proprietary systems now available, developed by the industry. AASHTO had a technical implementation group, and then the big story came about when the SHARP 2 started funding many of these renewal projects. There was a study, actually I was part of that study from 2008 to 2012 to look at the precast concrete pavement technology and to develop guidelines and so forth, model specifications, and to determine in the field how these projects were performing. So there's a good report available at the SHARP website, and based on the findings from that study, FHW and the SHARP 2 and AASHTO have now sponsored an implementation program funding this wider implementation of technology to different state agencies. So as part of this program, again, I'm involved in that. FHW is providing tech support as well as some financial support to do demonstration projects for state agencies that have never done any of these precast projects. As I mentioned before, there are some states that are routinely using it, but there are still many states that can use this technology. So when do we use it? Traffic volume is the critical part here. Many of our highways are carrying 100,000 to 200,000 vehicles per day. That's very significant. If you have low volume roadways, we are probably not looking at this as a good technology for those conditions. But anytime you've got more than 50,000 vehicles per day using the facility, this is the right application. So is it heavy enough to preclude other pavement alternatives? If fast track or cast-in-place slip-on paving techniques are possible, maybe this is not a right application because it is slightly expensive. Alternate routes. If traffic can be staged or detoured, maybe, again, this technology may not be as cost-effective. But if you have only 8 hours or less of lane closures, typically at night, you need to strongly consider precast pavements. Okay? And that's the situation in most urban areas. So primary application, 90% of the use is for heavily traveled mainline interstate primary system, ramps and so forth. And then we are also now doing special applications to intersections, bridge approach slabs, bus pads. Many airport authorities are looking at it also for gate replacement, pavement replacement at gates and intersections and so forth. So these are the applications. 2 types of application. The intermittent repairs, this is what we refer to as full depth repairs or full panel replacement, and longer length or continuous application. We can be replacing a ramp or a lane, a truck lane, or multiple lanes, depending on your situation. So we'll refer to this as intermittent repairs or continuous application. So systems we have available, typically we are using panels, full width panels. The length may depend on your need. If it's a full depth repair, some have used as short length as 6 foot. Typically it's 8 foot to 10 foot to full slab length. The panels are typically reinforced. They can also be pre-stressed to get you more structural capacity in a given cross-section. For continuous application, again, for jointed systems, we have, again, the same situation, reinforced or pre-stressed panels. But we also have post-tension systems where we connect 20 or more panels to give us a longer length without joints or active joints. So at the end of this connected section, post-tension section, we have an expansion joint. So we can have a length of about 200 to 250 foot long, an expansion joint, and an additional length, and so forth. We have other systems that has not been really tried, but referred to as internally incrementally connected system. This simulates what in the old days we used to call jointed reinforced concrete pavement. I'm not going to discuss that. But as indicated here, we have generic as well as proprietary systems. The generic systems are typically systems funded by Federal Highway developer using funding from Federal Highway Administration or state DOT developed systems. Okay, so this is some schematics. So when we are doing the repair, most of the steps are very similar to what we do currently. The only difference is instead of having a ready-mix truck that gets probably stuck in traffic, and then truck comes out there, contractors add water into it and finish up the work. We get poor quality, poor performance, but here all the steps are similar. We just bring the panel that's already at full strength. So the question of concrete durability is no longer there. We don't have to worry about workability or poor construction at the site. We still have to prepare the base. We still have to provide for load transfer at the joints. So the panel may come with dowel bars embedded, and we cut slots in the existing, or we may drill and grout dowel bars and bring a panel with slots at the bottom. Okay, so we've got different options. And when we do continuous application, we are basically connecting panels one to the next and so forth. Okay, and we can have slots at the bottom, we can have slots at the top, as shown here. So different systems. This is a New York-based system. Here, the panels are typically always the same. They're all reinforced. The dowel bar detail may be different. So here, the panel, the standard panel, the site is prepared, the hole is prepared, the panel is brought, placed in the hole. The difference is it's placed 1 inch below the final surface. And then the pump urethane-type polyurethane foam bedding under the slab, lift the slab up that 1 inch, and once that's done, they come back and do the slots for the dowel bar. So this is what we would call, if it's a dowel bar retrofit type application. So this would be a full dowel bar retrofit load transfer application. This is an Illinois tollway generic system. In Chicago area, the contractors didn't want to use proprietary systems, so the DOT developed a generic system, keep it in-house, and basically they have a reinforced panel, they bring it, do the same thing like here, prepare the site, place the panel in, except the panel is placed on a prepared bedding. So it's right at the grade, then they come in, they make that slots, or the panels will come in with the slots. Okay. This is one of the most widely used systems and the first production developed system by Fort Miller Company, referred to as super slab. They came up with this idea of slots at the bottom, and then in repair applications, the dowel bars are drilled into an existing pavement, and then the panel is placed right over it. They come back later on and pour fast-setting, high-strength grout in the slot, and that's what it will look like. When you use it in a continuous environment, then basically you are placing one panel with a slot. The next panel will have dowel bars, and you build up your length that way. This is a system developed in California recently. And basically here, we are bringing in the panel, and we are keeping it elevated by about an inch. So we are controlling the elevation using this leveling lift device. It's a screw-type device. Okay? The reason for that is in any of the other systems, when we're placing the panel, there's always some elevation difference at the joint. So we have to come back and do grinding. Okay? Here, the idea is that you control the elevation, if it's a repair or a continuous, using this leveling rod, and you never have to go and do grinding, or you shouldn't have to do the grinding. So there is a gap, and the other innovation is that they use a sliding dowel concept. So the panel is placed in the hole. There is a hole in the adjacent panel, a hole, or if it's an existing, a drill hole. And once the panel is placed, they slide the dowel into the other hole, and then come back and patch the dowel hole. And then they use a rapid setting grout. So if everything works right, you can set the panels, level it, take care of the dowel bar and the grout, and put the bedding grout all the same night. All of this work starts at about 8 or 9 p.m. You are open to traffic by 5 or 6 a.m. next day. So some more views of that. This is the leveling system, the screw system. It's the dowel bars. They're slid into the adjacent hole. Okay. This is the post-tensioning system. I won't dwell too much on it because of the time. This was the original system. Basically, we are bringing 20, 25 panels together, 10 foot long, and post-tensioning them. Okay. The next version, we are from the central stressing pocket. In the next version, we are doing post-tensioning from the end pockets, the expansion joint panels. In the current version, we are actually doing the post-tensioning. We're maintaining a gap and doing post-tensioning from the side joint face. Okay, so 3 different schemes. This is being used in California. This was an original one in the first project in Texas. So different views of the post-tension system. We can also build in the cross-section. Again, whether it's post-tension or jointed, we can have whatever cross-section we want, okay, tapered panel, or whatever. One of the version in California, instead of 25 10-foot panels, they use 36-foot long panel and use 6 of them to give us a post-tension length of 216 foot. So they just had to place 6 panels instead of 22 panels. So it's a lot of time. Every panel you place and position takes so many minutes. So the fewer steps you have to do, the more efficient you are. So some comparison between jointed and the pre-stressed system, precast. For jointed, we are basically all the thickness and joint spacing are very similar to what we do for cast in place. For the pre-stressed system, precast pre-stress, we build in an effective pre-stress of about 200 psi by post-tensioning. So it gives an advantage, and we can reduce the thickness. So it's almost like having 200 psi extra strength in the concrete, and we can reduce the thickness. So we can use 8 to 10 inches compared to 10 to 14 inches, and so forth. Used now widely, routinely used California, Illinois, Toledo, and some of the states here, Ontario and Quebec. Many states have done demonstration project. Anybody from Kansas here? There's a project coming up this summer near Fort Leavenworth, the prison, the roadway in front of the prison. And as I mentioned before, other countries have also used this technology for more longer than us. Very quickly, I know I'm going to run out of time. So panel placement rate. or fabrication. We can do about 8 to 10 panels in a precast yard, inside or outside. Okay? This is the typical, based on projects that we have going on right now. And the same thing for the post-tension type panels. When we do repair of insulation, we are placing 15 to 20 panels per night, or we can do that. We have done that. When we are doing jointed, we are placing 30 to 40 panels per night at 15 foot per panel. It comes to about 500 to 600 foot. So every night we can do 500 to 600 foot placement. And the same thing for post-tension. So several weeks of backlog of panels is needed. So you have to build up your backlog of panels before you get to the site. So once you award a project, there is a delay of so many months. So the contractor can build up the supply of panels. And some of these panels could be custom panels if you are going around a curve or something like that. So in future, we are looking at 30 to 40 repair panels or 1,000 foot of production. So we really would have to gear up in the fabrication or have multiple precasters come into play. Different installation, typically we are doing, or conventionally we have done precast panel, place it on a prepared base. We have done, this is the one I was talking about. We place the panel an inch below and then pump polyurethane. It expands, raises the panel to the right elevation. This is another, the leveling lift system that I was talking about in California. Basically, you are setting the panel, maintaining elevation, then coming back with rapid setting grout. And in all cases, we are always using dowel bars, whatever mechanism we use, full dowel bar retrofit or partial dowel bar retrofit, and so forth. So key requirements, concrete, we have taken care of it. We do it in precast plant. I've seen now projects where the contractor is doing precasting using wood forms on the side of a roadway. Okay. If we start getting back into poor quality control, it's going to create issues for the performance. But if it's coming from the precast plant, certified plants, and so forth, we have no problems with concrete quality. We need to pay attention to jointing, support condition, and of course surface characteristics, smoothness, and texture. Concrete, we are using slump concrete depending on the contractor, or self-consolidating concrete. We are using reinforcement, or as the panel gets longer or wider, we have to do pre-tensioning to accommodate the tensile stresses that develop, because we are basically stripping off the forms the next day within 16 hours. So the concrete has to have the strength so it can be lifted out. So the size of your panel affects what you do with reinforcement and the pre-tensioning. Load transfer, again, I'm not going to get into too many details, just to show we are, in all cases, we are using a slat system, slat at the bottom, slat at the top, depending on whether it's a generic system or a proprietary system. Support condition, we're almost always repairing or rehabilitating an existing pavement. So we are dealing with whatever is there. If you have to do major reworking of the support base and subgrade, probably not a good technique, or you will have to have some different types of lane closure requirements. Okay? Here we are just removing the bed concrete or asphalt, reworking a little bit on the base, then be making up some little bit more of the base with cement-treated base or rapid setting lean concrete base, and going with that. So the base needs to be, the support condition needs to be reasonably good for us to do this within that short lane closure period between 8 o'clock and 5 o'clock in the morning. Just a recent example, Hawaii. Okay, I'm just going to go through this. So we are doing some repair work here. This pavement had settled, and they've been doing some asphalt overlaying on a short section. Hawaii is using this project to determine whether it's a good candidate for them or not. So anyway, here This is, let's say, afternoon. This is traffic going to Honolulu by the airport. So there is a rush hour is in this direction, early morning. So by afternoon, traffic eases off. They can shut down 2 lanes or whatever and start working, removing the existing pavement, grading and so forth. At nighttime, they've got the grade ready. They're using the leveling lift California system. Requires some preparatory work. They bring in the panel, and the panels are placed. Dowel bars are positioned, bedding grout is applied, and so forth. The next morning, it's open to traffic. So this is an actual condition, situation. Illinois Tollway is going to be using precast panels for approach slabs in some of these integral bridges, where the bridge and the abutment is all in one system. They've been having problems with cast-in-place approach slab. They're developing some cracking when they use cast-in-place approach slab. So they want to use precast panels for that. So the early cracking problem will not develop. This is a project coming up in Texas intersection. This is an energy road type project where heavy trucks are using a road that was not designed for such. This is the Shell oil area. And so they're going to be using precast panels for a lot of their intersections if this demonstration project works. So this project is coming up if you're in the Texas area sometime this summer. This is a bus bed. So if you have urban areas, asphalt bus beds that don't work, you can come in overnight, take out the asphalt, put in the panels, 4 or 5 panels. Next morning, you're ready to go. Thank you very much.
Thank you. Any questions?
Compare it, just the raw cost. I mean, there are user costs and things that, but this is typically a lot more expensive than, regular construction. Do you have a feeling if you're to compare?
Yeah, no, I can.
Yeah.
So I didn't get into that, but basically when we started using this in 2001, the panels or the installation and everything was costing us about $900 per square yard. Compared to that, rapid setting concrete repairs and rehabilitation was costing us about, let's say, $250 to $300 per square yard. Over the last 10, 12 years, the cost is now, with the precast, about $350 to $400 per square yard. The rapid setting is now $300 to whatever, around that. So the costs have narrowed. And this is much better, risk-free, and safe operation.
Okay. Very interesting.
Yes?
Yes, sir.
Oh, yeah. I mean, in the sense that when we had that SHARP 2 study, we did go out. There was that question that we have had all this demonstration project, and some states have already started using it. How are they performing? So we actually made a deliberate attempt and went and tested 16 of these projects. And it's all given in the report. But basically, they're performing fine. Take my word for it. Okay? We had a few failures, but we know why.
Thank you.